This is for anybody who is either in mineralogy, has taken mineralogy, will take mineralogy, or has any interest in minerals. After I first created this deep dive of what you're about to listen to, I was both jealous of my future listeners who are currently in school, as well as reassured about how much of my mineralogy class I remember. Mineralogy comes up in my life all the time. Honestly, I think mineralogy should be a required course at university. To be a person, to go through life without understanding the fundamental building blocks of the world around you. At the age of 20, I stopped having that experience. This is a deep dive into William D. Nesse's Introduction to Mineralogy. After listening to this deep dive myself for the first time, I felt like had I had this resource at my disposal, I would have gotten A plus in my mineralogy class. As it stands, I got a B. Mineralogy was probably one of my toughest classes. However, it was one of my most enjoyable classes as well. I really enjoyed the lab that is part of mineralogy, as you're actually given hand samples to learn how to identify these different hand samples. And every week we had 30 minerals that we had to learn, memorize, and be able to identify. At the end of the week, the TA would give us 30 different samples of that same mineral. So we couldn't just memorize the rock. Basically, three kind of phases for my mineralogy class. One was a hand sample. Two was thin section. So they would take a rock, slice it, glue it to a glass slide for a microscope with super glue, then shave the other side of the rock, and then grind down that rock that's left glued to that slide until that rock is so razor thin that light can pass through it all. And that's called a thin section mount. And we had to learn, identify these minerals and memorize these minerals as seen through a microscope. The other aspect of mineralogy is actually learning shapes. At the moment when I was first getting into it, I was like, come on, we know shapes, until they pass you a tetrahedron. You get to learn a lot about geometry in mineralogy. The last year and a half of my life has been all about geometry because I was involved with the Escher estate. And so long story short, you can show me a picture of any Escher and I can pretty much tell you the name of it. A lot of factoids about it. Yeah, try me anything Escher. That's a new expertise that I have. As a geologist who has a great love of mineralogy, Escher is fascinating. Tessellations exist inside of mineralogy, like inside the minerals, fundamental building blocks of inorganic compounds. Anyway, I've talked too much. Enjoy this deep dive.
We're taking a look at chapter 1 from this mineralogy textbook to really get a grasp on the fundamentals of minerals.
A lot of people just think about like rocks and gems, but to be a mineral scientifically, it has to be naturally occurring, so it forms on its own out there in the environment.
So those synthetic crystals that they grow in labs, those wouldn't qualify as minerals, would they? Because that involves human intervention.
Exactly, and on top of that, a mineral has to have a defined crystalline structure, so its atoms have to be arranged in a specific repeating pattern.
It's that internal structure that is responsible for the beautiful and sometimes symmetrical shapes we see in crystals.
Right, the textbook mentions the chemical composition is important too. Each mineral has a very specific chemical formula, like quartz, which is SiO2.
That makes sense, but I did notice that the textbook says the composition doesn't have to be fixed in every case.
There's some wiggle room there.
Yep.
Take olivine, for instance. It can have different amounts of iron or magnesium, but the overall ratio to silicon and oxygen always stays the same.
It's so interesting how there can be these variations even at the atomic level, which then leads to such a diversity in the mineral world.
And, even seashells are considered minerals. Theirs are made of calcite or aragonite, and even our own bones and teeth contain apatite.
So that really challenges that traditional idea that minerals have to be inorganic. I mean, biological processes create minerals all the time.
Bacteria can even get involved in forming minerals like pyrite, which you'll often find in coal beds.
But there are also these substances that kind of look like minerals, but they're classified as mineraloids, right? Because they don't have that consistent crystalline structure.
Mineraloids can have a lot of mineral-like qualities, but their internal arrangement just isn't organized in that repeating long-range structure that minerals have.
Opal is a great example of a mineraloid because it's made of silica, but it just doesn't have that rigid crystal arrangement that you see in quartz.
Volcanic glass is another one. It's formed when molten lava cools down so quickly that the atoms don't have time to arrange themselves into that crystal lattice.
And even more dramatic events can create mineraloids, like the glass that's formed during meteorite impacts.
Lightning strikes can even create mineraloids. These are called fulgurites. It's when the lightning melts and fuses soil or rock into a glassy material.
And then there are the minerals that actually transition into mineraloids over time through this process called metamictization.
That happens when radioactive decay disrupts that once orderly arrangement of atoms inside the mineral, so it's essentially transforming it into a mineraloid.
So let's shift gears a bit and talk about how we learn about all of this. It seems like our relationship with minerals goes way, way back.
Oh yeah, ancient civilizations were using minerals for practical purposes long before anybody formally studied them.
And I imagine they were probably drawn to minerals for pretty basic reasons like their strength for building or, their beautiful colors for decoration.
But the formal study of minerals that can be traced back to a Greek scholar named Theophrastus around 300 BC, he wrote a book called On Stones.
Then centuries later, Pliny the Elder provided a pretty thorough overview of how the Roman Empire used minerals, these for ores, gemstones, pigments, even medicines.
And in the 16th century, Georgius Agricola, he was a German physician and mining engineer, he was the one who introduced terms like hardness and cleavage.
And those are still terms that we use today to describe mineral properties, right? And they were crucial for developing ways to classify minerals.
But the most revolutionary change in how we understand minerals came in the 20th century with X-rays.
In 1912, Max von Laue showed that crystals could diffract X-rays, proving that they have this incredibly ordered internal structure.
Before that, we could only see the outside of minerals, their external features. But with X-rays, we could suddenly see inside and understand how those atoms are arranged.
And just a few years later, W.H. Bragg and his son, W.L. Bragg, they used X-rays to figure out the actual crystal structure of a whole bunch of different minerals.
And after that, they developed a whole bunch of new tools and techniques to study the chemistry of minerals and how they behave in different geological settings.
It really is amazing how far we've come from just observing minerals to being able to analyze their tiniest details, their structure and composition.
And that's what has let us identify over 3,500 different mineral species. But of course, only a small number of those are the ones that we come across in everyday life.
And so when scientists think they've discovered a new mineral, there's a very strict process that has to be followed.
They have to prove that it really is a new mineral by analyzing the crystal structure and chemical composition. And they also have to preserve what's called a type sample.
And that ensures that future scientists will have a reference point for comparison. It's interesting to think about how minerals get their names.
Sometimes they are named after the person who found them or the place where they were discovered.
Some minerals get their names based on a specific property, like their color or chemical composition. And then there are some minerals with names that come from ancient history.
Each mineral has its own unique story to tell about the Earth's formation and all the geological processes that keep happening.
Minerals really are the building blocks of our planet, and they play a role in pretty much everything we do.
Everything that we take out of the ground and even the soil that we depend on for growing crops, it's all connected to minerals in some way.
Yeah, and understanding the properties of minerals, that's super important in construction because the safety and stability of buildings depends on knowing about the rocks and soil that they're built on.
And minerals, they're like a window into the history of Earth because by looking at their composition and structure and texture, geologists can kind of put together how our planet has evolved over time.
It's like they're time capsules, aren't they?
Yeah.
They hold these records of geological events that have happened over millions or even billions of years.
As we keep studying and learning more about minerals, we're bound to discover more secrets about the Earth's past, present, and future.
It's pretty amazing how much information we can get from something as seemingly simple as a rock.
It shows how everything in nature is connected from the smallest atom to the largest mountain range. It's all part of this really complex and dynamic system.
Learning about minerals, it really does change how you see the world around you.
Every rock and gemstone and even materials used in buildings, they all tell a story about the minerals that are in them.
And it gives you this new appreciation for the ground we're standing on, literally.
It's true. These insights into the mineral world, they really highlight how connected everything is from the very ground beneath our feet to the structures that we build, and it really makes you think about the materials that we use in our daily lives in a whole new way.
It's definitely a reminder that we're all part of this incredible interconnected system, and that even something as simple as a mineral can hold so much information about our planet and its history.